I'd like to do a second example using the alternating series test, not because the test is particularly hard, but to show you a slightly different behavior than what we saw in the previous example. So the next series I would like to consider is the alternating series that starts at n and goes to infinity and has just an n in the denominator. And what I would like to do is actually compare this to the behavior of a different series, where this series has as its addends the absolute value of the addends in our alternating series. Again, we check to see whether or not this series is alternating by plugging in various values for n and seeing what the series looks like. 1 minus a half plus a third minus a fourth. And this is one of the series that we saw as an example of an alternating series on the first slide. So we see that this is indeed alternating. We've already discussed that when we take the absolute value of these terms, the absolute value of that alternator becomes just the number 1, and they become the terms of this series. And note that as n is getting very large, the limit of the absolute value of the addends in our alternating series is 0. Where I would like to differ from our previous example is in how we're going to go about showing that the absolute value of our terms are a decreasing sequence. Now, in order to do this one, we're going to actually use derivatives. With our previous example, we showed quite directly that the n plus first term was smaller in absolute value than the nth term, and we did that by plugging in values for n plus 1 and n. That was necessary in the previous example because we were dealing with factorials, and factorials are not a thing that we have a continuous analog of. However, when we're talking about something like 1 over n, if I blinked my eyes and changed the n's to x's, I could imagine that I'm living in a world of calculus where f of x is this nice continuous function on the interval from 1 to infinity, and is certainly something that I would know how to take the derivative of. I would change my representation of 1 over x to x to the negative first power. I'd differentiate using the power rule, and then rewrite this as a fraction just to make things a little more clear. In this fraction, the numerator is negative, it's always negative 1, and my denominator is x squared, which is always going to be a positive number on the interval that I'm considering. So the value of this derivative on my interval from 1 to infinity is that it is always negative. And what that means about my original function is that that function must be decreasing because it has a negative slope. So this is an alternative method that's a little bit more of a straightforward computation to show that we have something that's decreasing, but it can only be used when we have a continuous analog and we would know how to take derivatives of the thing that we're examining. This shows that this series is in fact an alternating series, that 1, the limit of the absolute value of its terms is 0, and 2, that the terms in absolute value are decreasing. And those are precisely the 3 conditions we needed in order for this series to be convergent by the alternating series test. So the series we're looking at right here, 1 minus a half plus a third minus a fourth, is a convergent series. In fact, somewhat shockingly, it adds up to the natural log of 2, which is something we'll see much further in the course, but is another shocking sum of a series. However, we had seen previously that this series is a divergent p-series because our p-value is precisely equal to 1, and our p-series diverge whenever that power is less than or equal to 1. So the effect that this alternator has had on the series is significant enough to change a divergent series into a convergent series. And so this example of a series where the given alternating series converges, but if you were to replace its addends with their absolute values and consider this series, and you got a divergent series, that's called a conditionally convergent alternating series, where the name is meant to be indicative of the fact that the convergence of the alternating series is conditional upon having the alternator present. Now that can be a little frustrating and a little scary. Another thing that's a little bit frustrating about the alternating series test is that I've made a big point to say that just because the limit of your terms is 0 does not mean you are a convergent series. And yet, for alternating series, having a limit of your terms be 0 is in fact essential and very much part of being a convergent series. So it's very, very frustrating, but it is important to keep these subtleties straight. So the two examples that we've considered in the first video and in this video are examples of absolutely convergent and conditionally convergent series. Now we haven't seen the tools just yet, but the first example we did where we considered the alternating series that had a 1 over n factorial but was alternating in it, that was a convergent series that we showed in the first video. We don't have the tools yet to show, but it is in fact true that if I were to take the absolute value of those terms and just look at 1 plus a half plus a sixth plus 1/24 plus and so on, that would also be a convergent series. So that type of series is called an absolutely convergent series because even if you were to take the absolute value of your addends, you would still get a convergent series. But the alternating harmonic series, the example we just did, is called conditionally convergent because the only reason that we're converging is because we satisfy the condition of being an alternating series. If we take the absolute value of those terms and look at the similar series that we get from doing that, we get a divergent series. So those are the words that you'll hear thrown around a lot. Is this an absolutely convergent series or a conditionally convergent series? Now the last thing I'll say here is that if you do have an absolutely convergent series and you were able to just take the absolute value of the terms and apply a different series test to show that that series is convergent, then you don't even need to perform the alternating series test because what we'll have is something very similar to a direct comparison test. If we take the absolute value of each of the addends and we end up with a convergent series, then certainly our original alternating series has a value that is less than the value of this other series that has larger terms. Whenever we take the absolute value of a term, it's either going to be exactly the same or it will be larger. And so when you have an absolutely convergent series, you don't even need to perform your alternating series test, which is something that we'll occasionally do in the future.